Oh yeah, it looks like we've reached the point here now where a whole lot of the content's been conveyed, and most of the rest of the content is going to come through examples. There's still going to be some board stuff, but it's going to be a lot more examples now. I like to front load the courses that involve a big project at the end. That way, once we hit the halfway point, there's less time spent taking notes in a lecture and more time spent working on your final project. So, well, first off, going back to the microphones, you may have noticed that, and this is a remake of Lecture 1, Module 5, Lecture 1, because my schedule is very tight, and some people, well, over the summer, while there was a lot more time, I tried some things, thought I found something acceptable, and some people, some complaints had been made about that, and I realized when I was testing things, I was testing it through really good speakers. And when I went back after hearing some complaints, went back and unplugged the really good speakers, I could tell very quickly what people were talking about. So I had to go back and test some more things, but my schedule is very tight. So the only time I had to test it was while making the video. So in the slot on the schedule that said make Module 5 lectures was the only time I had for testing, and I wasn't sure if I was going to be able to find time to remake it. And obviously here I did find time to remake it. Hopefully the audio quality is a lot better now. I've gone back to these type of headphones, the necklace-like ones, super comfortable. My other options is I have high quality stuff, the sort of equipment that should be run by an entire crew, which is kind of difficult to run with just a single person, and it takes 3 or 4 times as long. So hopefully I won't have to go back to that. Hopefully this is going to improve this audio quality so that everything can be made in a reasonable amount of time and y'all can hear the information. And I think I got everything worked out, but I needed to remake those videos where I did all the testing at. So that's where we're at today. Hopefully it's coming across better and all the settings are right. My lips are moving at the same time the sound's coming, and everything's worked out now. So I'm going to run with this setup for a while because it seemed to go a lot better in both the good and the lousy speakers. So we're up to the point that most of the content is going to come in the way of examples. So there's a lot of examples, and I'm not remaking the screencast part. The audio there was much better because I was sitting the same distance from the microphone the entire time. So there wasn't any problems with that audio. Just redoing the board parts for Module 5, Lecture 1. So where are we at here? We've been looking at the 4 constructs, the type of tools we have to solve problems. And, well, sequential, the order things go in, the sequence. That shows up everywhere. We get lots of practice with that. Invocation, where we can leave our sequence and then come back to it. We saw how to do that, at least introduction. There's still some more things we could talk about with it that'll be worked into the examples from here on out. But hopefully the core idea of it's there. Last week we looked at the selection structures, making choices, taking different branches through a sequence. So there's one more of our 4 constructs we haven't talked about yet, the reiterative structures. So that's what we're going to talk about today. And this is the same content as the original video. I'm going to label them original and remake and put a note in the description. So you won't need to watch both. But at the same time, what I call a script is a stack of Post-it notes. So I'm not saying things the exact same way. Maybe I said something better that you'll relate to in the first video, even though there was a lag with the microphone. So if you have time, it wouldn't hurt to check out some of those scenes. But it should be better in this one and talking about the same general content. So there's no need to watch both of them. But talking about reiterative structures, and we're going to look at what we always have in machines, what machines do naturally to repeat things. And then which can be kind of difficult. So after that, we're going to look at 2 tools that are available in most programming languages that make it a whole lot easier. So let's get started into that. So we're going to look at 3 different ways of repeating things, reiterating things. And so that we can focus on the tools that we're using, I'm going to use the same example for all 3. So I decided to go with Factorials, which is a math operation. You may have seen it when I was in elementary school and being introduced to multiplication for the very first time. The teacher showed us some simple examples of factorials leading up to, I don't think we got bigger than 7. Other people that I've talked to have said they did not see that then, and yet other people said they also saw that when they were learning multiplication. You may have saw that way back in elementary school, but it didn't. For some of us, it shows up in 3rd or 4th grade when we're first learning to multiply, and then it does not show back up until a Calculus 2 class. So if you haven't had Calc 2, you may not have seen that. Our symbol for the operation is an exclamation point. And what it means is we're going to multiply all the numbers up to the one in question. So 5 factorial, that's the number we get when we take 5 times 4 times 3 times 2 times 1. And obviously times 1 at the end doesn't do anything. It just doesn't make any sense to stop the pattern at 2. So we go all the way down. So 5 times 4 times 3 times 2 times 1. So that's 20 times 3 is 60, times 2 is 120, times 1 doesn't change anything. So 5 factorial comes out to 120. So we just multiply. So 5 factorial is all the numbers multiplied until we get to 5. 5 and then everything down. And we have this special definition, 0 factorial is equal to 1. That's just part of the definition of the operation. We want to include 0. And there's another thing we can do with fractions and negative numbers that is not factorial, but it uses the same notation and follows the same thing. But we're only talking about our positive integers, so or our non-negative integers, because we include 0. So 0 and then the positive whole numbers are what we're going to use for factorials. And it's just all the numbers leading up to the number multiplied together. So like 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So a whole bunch of numbers multiplied together. And an important thing to note, it'll show up here in a moment, is inside of 7 factorial, we have 5 factorial. So one thing about factorials, whatever number we're looking at, the factorial of every number smaller than that is included. So since all I have wrote up here is 5, another way to write this would be 7 times 6 times 5 factorial. Could have done 6 as well, but I don't have that wrote on the board. And we know what 5 factorial is. So that's like 7 times 6 times 120. So that comes out that big when I happen to have this memorized. That's 5,040. Once you get up to Calculus 2 and see that, and then in subsequent classes, it tends to show up a lot. So some of the small ones tend to, especially the things that are going to show up in combinatorics that we could count on our fingers, I have all those memorized. But the key point is what it means. 0 factorial means 1. We just defined that one. Then any other number, the factorial is all the numbers leading up to that multiplied together. Which a result of that is any factorial could be written as that number times the next number down, the factorial of the next number down. So like 5 factorial could be written as 5 times 4 factorial. And then 4 factorial could be written as could be written as 4 times 3 factorial, and so on, all the way down, or all the way up. But these numbers get very, very large very, very quickly. So when we put these programs together and you're testing things, test with small numbers. You can see going from 5 to 7, we went from 120 to 5,040. Or 101 in base 10. It's not that big of a number, right? We've only barely reached 3 digits. Well, that's approximately 9.43 times 10, times 10 to the 159th power. An absolutely huge number. This is about what we would get if we took the number of atoms in the universe and squared that number. So these get very, very big very, very quickly. So when we're testing program, test with small numbers. You'll hit the overflow error fairly quickly. Well, actually, we're at the introduction level, so maybe hit a couple overflow errors so you see what those look like. Because when we hit the limit of what can be stored, if we're working in, say, 32-bit integers, there's an upper limit to what we can store there. What happens if we pass that limit? That's called an overflow error. So maybe throw in some big numbers and see what happens when you get an overflow error. But this is the math we're going to use on all our examples. That way, we're looking at the same example, and we can focus on the tool itself we're using to solve the problem. So factorials. Whoops, I almost forgot to write the generic form that we'll actually need to put the program together. I'm going to erase some of this. Well, I'll put it over here. So for any number we're looking at, the factorial of that number, our general formula for it, is going to be that number multiplied by 1 less than that number, multiplied by 2 less than that number, and so on and so forth. I did run out of room. And we'll just keep repeating that. Just keep subtracting 1 until we get all the way down. N minus n, which would be 0, plus 1. So we're going to start with our number, and just whatever number we start with, we'll multiply that by 1 less, and multiply by 2 less, and 3 less, and 4 less, and 5 less. However many there is until we get all the way down to 1. And that's the general formula we're going to use to program the computer. Okay, so the first one we're going to look at here is what machines do naturally. What innate property of machines do we have so that some repetition can occur? Well, if we think about a machine, kind of drew a picture like this a couple times, right? Our basic, the basic starting point we've drawn up here a couple times. We get some input, stuff happens, then we get some output. Well, one thing we can always do is, well, I drew that with an arrow because we're sending it somewhere. And one place we can always send that is back to our input. When that happens, it's called feedback. And you've probably heard that term before, right? So let's think about where that term shows up most often in our common culture. Most often place you've probably heard of it is, let's say, we have somebody singing, and their voice goes into a microphone. Well, an electrical signal goes down, comes over, gets amplified, and comes back out a speaker a little bit louder. That way it fills up the room nicely. A large, in a large auditorium, everybody can hear the person singing clearly. But there's a chance that that sound could go right back in that microphone. That sound could just hit the microphone again, in which case it would go down the line, get amplified, come back out the speaker louder. And once again, go back into the microphone, down the line, get amplified, come out louder, back in the microphone, and before long, the room is just filled with this annoying screeching sound from the sound getting amplified, going back in the microphone, getting amplified, and then that repetition of that same sound just getting amplified over and over and over again, getting amplified and going back into the input. That's audio feedback, usually an annoyance. But some musicians, the first two that always spring to my mind would be Jimi Hendrix and Tom Morello, because they did it exceptionally well. But for them, feedback was just another note that their guitar played. They learned to control that feedback, and then periodically that was a note they wanted to put in the song they were playing. But it can be controlled. It's not just an annoyance. And when we control it, when we actually control the feedback in programming, we're going to call that recursion. I'm going to erase this little picture I originally put here. But the basic idea of feedback is our output goes to the input. So recursion is controlled feedback in programming to create a reiterative structure. So when we control feedback through our program, we can make it form a reiterative structure. And in that case, it's called recursion. So there are some criteria we have to meet in order to do this. Because, well, like the inputs and outputs we've seen so far in Raptor, the examples we're using, is it pops up a dialog box that the user types into for the input, and then the output goes to the console. We don't have a way directly to take that console stuff and send it back to the input. So most of what we've done so far is not going to work for that. And there's some criteria. Things have to be set up in a certain order so that we can control that feedback. So our criteria is, the first thing, the problem must reduce to a simpler version of itself, or a smaller version of itself. So we have to take whatever problem we're trying to solve and find a solution for it that is essentially a smaller version of the same problem. Such as in the factorial thing, where I pointed out that 7 factorial, well, another way we could think of that is 7 times 6 factorial. So it reduces to a smaller version of the original problem. We still have a factorial there to solve, just a smaller one. So that's our first criteria. And the second thing that has to be met in order to use recursion is we cannot do this indefinitely. We can't go on forever this way. The problem eventually has to stop. The problem must reduce to a base case. There eventually has to be a smallest version of this problem, which with that example of factorials, we define that thing, 0 factorial equals 1. We eventually hit a definition where it's definitely solved. We're not going to break that down any further. Or we could stop at 1. Because 1 factorial is we multiply all the numbers together until we get to 1. Or until we get up to the number we asked for. So starting at 1 and going to the number we asked for, 1. Well, we're done. That cannot be written any smaller. So there is a stopping point, a base case that it eventually, this reduction over and over and over again, eventually hits a stopping point. We have to have that in order to do recursion. And if both criteria are met, sometimes in computer science classes you'll see this listed as 3 criteria, but these are the 2 criteria we have to meet. And if both of those are met, I'll go ahead and label it this way. I'll go ahead and put a third on it, but they're kind of separate things. The third thing in order to be recursion is the solution must refer to itself. So the smaller and smaller problems, and eventually we hit a base case. So really what we do is we solve the base case. And anything that's not the base case, we just ask again until we keep asking for that solution over and over and over again, and then it kind of works through. Hopefully that'll make more sense whenever we see an example here very, very shortly. But these 2 criteria, once we meet those, we have the problem we're trying to solve in a fashion that can be reduced to a smaller version of itself and does eventually have a stopping point. Well, then if we can develop a solution that refers to itself, then we have recursion, our basic reiterative structure for machines that is always available. This is natural to machines, so we always have this option. The thing is, like that example, I was pointing at those factorials because they naturally fall into that. Most of the problems we're going to try to solve, we have to do a whole lot of reformatting and thinking really, really hard to get it to meet these criteria. So it can be difficult. But a lot of problems can be organized this way quite easily. And it is difficult. I've been told repeatedly I kind of have a knack for setting things up in recursion. It doesn't seem that way. It's still really hard. But any problem can be reformulated this way. It just gets very difficult at times. So whenever we have problems that kind of naturally fall into these criteria, then recursion is a better option to do that. And some of our programming languages don't have, some of our programming languages, this is the only way we have to form a reiterative structure. But if our criteria are met, the problem can be formulated in such a way that it reduces to a smaller version of itself, which will eventually stop reducing. Then we can put together a solution that refers to itself and control the feedback in order to have recursion. Let's go look at an example of this.
Okay, so over here in Raptor now and ready to do this. But one thing we haven't seen yet is from this process of recursion, we need feedback. We need our output to go to the input. So in order to do that, we need very well-defined inputs and outputs, and not just asking the user or throwing it up to the console. Because, well, if we're throwing it to the console, we can't send that back to the ask the user box. So it's similar to subcharts. And remember when we talk about subcharts, those are just kind of a breakout thing. They just take a chunk of the one we're in and put it in another spot just to organize it nicely. We need to actually leave and do something else, and that's where procedures come in. So make sure that you're in intermediate mode. So go to mode and select intermediate mode, and then you'll have a button for procedure. So we'll add a procedure, and then we get this little box. What are we going to call it? Well, we're going to call this Factorial because we're solving factorials. And here's where we can introduce our feedback loop, feedback to this. We have very well-defined inputs and outputs being passed back and forth in the background. So for a factorial, well, we really just need to know what number we're taking the factorial of. So I'll call it number. And that will be an input. And then after we solve that, we want to send back the result of that. We want to send back the result. So in this next box, I'm going to uncheck input and send back an output. And I'll call that fact, just an abbreviation of that to avoid using the same word twice. So we're going to pass in the number we want the factorial of, do the processing, and then send back this other thing called fact. So you can see here in the other tab, now our little start bubble has some extra stuff in it. It's taking in a number and returning a number. So first off, I guess we can look at calling this in the end. So let's go ahead and fill out the process for making a factorial. So that first criteria listed was to do things recursively, it has to reach a base case, which for factorial will be when we get all the way down to 1. Okay? So 5 factorial, we're going to take 5 times 4 times 3 times 2 times 1. And then when we get down to 1, we'll be done. So we'll bring in a selection structure, and we need to see if we're above 1. So that value we passed in, number, is that bigger than 1? Because if it's not bigger than 1, then that means we've reached our base case. So we can go ahead and return our base case. And our return thing, so fact, we want to return our base case of 1. And I mentioned on the board that we have that special definition that if the user gives us a 0, we're going to define 0 factorial as 1. We might want to, we could set things up to spell that out specifically, but here if we hit a 1 or a 0 or any negative numbers are just going to default to that. That's not really what negative numbers are, but we'll just kind of go down to the base case and try to keep the example simple. So when we get all the way down, so if it's not bigger than 1, our output is going to be that number 1, that number we've got down to. But if it's not bigger than 1, well, then we need to take whatever number it is and multiply it by the next smaller factorial. So we'll use the call statement to ask for factorial again. We'll ask for this factorial procedure again. So if we go in here, we want to call factorial, and we can see down here in the predictive, we're taking in a number. So like was written on the board, the next factorial we want to ask, so like 7 factorial was the example on the board. If we're at 7, well, we want to take our 7 and multiply it by 6 factorial. So we're going to ask for number minus 1. So we're going to send 1 less than whatever number we're looking at right back into this same procedure and see what the next smallest factorial is. And then keep doing that until we get down to the base case. And we're going to get back this thing called factorial. This thing called fact. So we're sending in 1 less than the number we're looking at, and we're getting back the result of that. And once we have that result, well, then we need to kind of reset it for the next return. So fact will be set to whatever we got back. So this is going to send us something back. I'm going to change the names here. Cancel this one. And I'm going to call this F. Calling that fact is what it was on the inside. So when I get it back, I'm going to put it in a spot called F. Because fact is what's actually being returned. So now we want to set that value that we're actually going to return, which we called fact, to F, which is what we got back here. So If we're not down to our base case, we're going to ask for the factorial of the next smallest number and get back what that is. So then once we get that back, we're going to find the factorial of the number we're looking at. The thing we actually return is that thing we got back multiplied by the number we're looking at. And that is what our method will look like. If we get all the way to our base case, we'll return a 1. If we're not to our base case, we'll ask for the next smallest factorial, and then whatever we get back from that multiplies by the number we're looking at. Let's give this a run and see what happens. So to call this, we'll come over to the main method, and we'll need a call statement to ask for that. I guess first off, we need to know what number the user would like to know the factorial of. So we'll ask the user for that. Which number do you want to know the factorial of? And again, you want to be very explicit in the prompts. Make sure it's very, very clear what the user is supposed to give you and how to input it. Well, floating point numbers don't work so well with factorials. That's a kind of a different thing. So let's make sure and say integer, which and negative numbers are also something different. So let's say positive integer. Which positive integer do you want to know the factorial of? And then whatever they give us, we'll call that user number. We'll store what they give us in a place called user number. Then once we have that, we can ask for the factorial of it. So we'll go to the call statement, and then we'll ask for that procedure we made, which is called factorial, and we're going to send in a number. Well, we're going to send in that number we just asked the user for, and we're going to get back something called, well, it's called fact on the inside, but we can call it something different here. So I'll call it user factorial. So we're sending in this number and getting back this number. So that's the difference between a subchart and a procedure. A procedure is completely separate. We have to send our variables and get them back. We can't just use the same ones over on the other tab, where we actually leave and come back. Well, once we have it, we'll send it out with some nicely labeled output. That way it's not like a magic number that seems to pop up out of nowhere, doesn't have any explanation. We want to make sure it's clear what that is. So we'll say the factorial of plus the number the user gave us, user number, plus is going to be plus, well, whatever we got back, user factorial. Did I spell something wrong? No, it's not in the predicted box. So notice that even though we have this variable, we'll put our what we're getting back in this variable called user factorial. It's not showing up in the predicted box. So now when we run this, well, first off, I'm going to turn the speed up and run it quickly so you can see the number come through. So if we run this, which positive integer do you want to know the factorial of? Well, in the lead-in, we used 5 in the example, so we know 5 factorials should be 120. So let's check that. The factorial of 5 is going to be 120. So yeah, that checked out. But let's slow this down and look at what's going on. And notice the watch window is a little bit different now. It labels which one of our charts we're in. It says in the main. So I'm going to slow this down and let's watch what happens as it goes through here. So we ask for the number. I'll enter a slightly bigger one. I'll do 7. That was the other example that kept showing up on the board. So we pass that in. And notice that it's bigger than 1, so it looks like it's not really changing here. But if we look over at the watch window, we have this stack. We're stacking up a whole bunch of these factorials. Oh, once we get down to 1, then we start passing things back. And it comes right back to where it was, and then just finishes out that piece of the stack. And here you can see those numbers get very big very quick. Going from 5 to 7, we went from 120 to 5,040. So I'm going to come over here and make some marks on here. So what's going on each time, if I turn on the ink, what color am I? Green, that might not show up so well. Undo that. Let's change that to red ink. That'll probably show up. Or we can use a couple colors. So once our main calls this the first time, we come in and like with the 7. It's bigger than 1, so we're going to go this way. And then factorial, first thing we're going to do is call factorial minus 1. So we're going to subtract 1, and then we're going to go right back into the factorial method with 1 less than what we did the first time, which was still bigger than 1. So again, we come through here, and again, first thing we hit is the factorial method, and we're going to call 1 less. So then, once again, we come back, call the next factorial, and we'll keep doing that with our number being 1 less each time. And eventually, we'll hit the base case. We'll get down all the way down to 1. And at that point, we'll take this branch. Oh, factorial, it's equal to 1. So we're going to set our output variable to 1 and then come on down to the end block. And once we hit the end block, well, it goes back to where it was. So then it'll jump to the most previous call statement and finish running through here. At that point, it reassigns what fact is again, hits the end, and goes back to the most recent call statement. Goes through there again, reassigns what fact is, hits the end, and goes back through. And that's going to keep repeating until we get all the way back to whatever our original number was. And at that point, it'll jump back over to the main. So let me clear that ink off there. I thought I had a clear button somewhere, but I can't remember where it's at. There we go. So let's run that again and watch it go through there again. So we run it. And let's check 12, a bigger number. Jumps in there. Well, 12 is bigger than 1, so it calls factorial again. And we end up with this stack of these calls, of these call functions. We keep calling factorial over and over and over again. And we get a bigger and bigger and bigger stack. And once we finally get to a result that we know that we're returning an output from, so fact1, then we just keep passing that back. And notice now that f variable is filled in. So then we can multiply that by the number that was passed in and keep going back to that spot we left the method from originally and end up with a very large number. So that's how recursion works. That one was probably very confusing, right? So really just introducing it here. Let's go back over to the board and talk some more about that. Recursion is what machines do naturally. So it can be faster. You may often hear in reference material recursion is going to be faster, but if you think about that, you'll quickly realize that that is kind of dependent on how nicely your code's written. Right? If you write really sloppy code that is terribly inefficient, that's going to slow recursion down as well. And then you have the nicely built things by really, really good programmers that wrote the programming language running pretty quickly. So the faster, you'll see in reference material that it's faster, but remember there's details there. Right? If you write really sloppy code, it's still good. It's going to go the speed of the sloppy code that you wrote. But it can be a lot faster because this is what the machine does naturally. But there's kind of an issue, right? That was probably a little complicated. And this example fell naturally into our criteria. Every pass of a factorial is, I can turn that off. Every pass of a factorial is a smaller example of a factorial. So this naturally met our criteria. But not every problem is going to.
Okay, so that's recursion. Once we meet our criteria, we can have the computer just repeat that until we reach the solution to a problem. It can be difficult at times, but that example was chosen because it naturally fits these criteria. Not every problem we're going to solve falls right into the criteria, and we have to reorganize and reformulate our algorithm until we find a way to put the algorithm that does meet these criteria, and that can be very difficult at times. So programmers that develop the software known as programming languages have given us another tool to work with, something called loops. And much like we looked at last week with our selection structure, where we have Boolean algebra conditional statements to determine which branch to take through a sequence, we can modify that slightly and have one of those branches just come back to that condition. And then the reiteration, the repetition, is determined based off a Boolean algebra condition, which is a whole lot easier to work with, because we can just come up with if there's not one in our problem, we can make up a completely separate one. We can just throw a counter in there and count how many times we do it. It's a much easier way to deal with, and we have it in most programming languages. Sometimes we don't have it. If we don't have it, we have to fall back to recursion. But in most of our programming languages, we do have the option to work with loops. So let's look at those now.